Welcome back for the second talk. Here we have a change in the last minute change in the program. Unfortunately, because of a health problem, Caio was not able to come, Caio Doria, and well, the next speaker is Gregory Cosac from USP, São Paulo, who will talk about semi-arithmetic Fuchsian groups and finiteness results.
Well, thank you, Misha, for the introduction and for the opportunity to speak here. For those of you who are expecting to see a talk by Doria, I'll try not to disappoint too much. So at least the subject is the same, semi-arithmetic Fuchsian groups. And so my goal is to define these objects, maybe say a couple of things that we know about these, and the hardest of all, to try to motivate a little bit as to why one would want to look into these things. Let me start with that last part. So as for motivation, one way to try to motivate this is to look at arithmetic groups, because arithmetic groups have been studied for, 60 plus years, and in particular arithmetic Fuchsian and Kleinian groups. And we know a lot about these objects. Perhaps not me, but the community knows a lot about these objects. And there are some things that we only know for these objects. And I have a very short list here. And this very short list, very non-comprehensive list of facts. So the first one is a very, very simple one. So the triangle, and don't worry about these because I'm going to define everything later on, but just as an introduction, the triangle group 237 is arithmetic, incidentally is arithmetic, and it happens to be the group of the smallest co-area. And as a consequence, every Riemann surface that has the maximum possible cardinality, whose group of isometries have the maximum possible cardinality, will have to cover this orbifold and will also be arithmetic. Those are called Hurwitz surfaces. So this is one instance of where arithmetic groups pop up. Number two, Boozer and Sarnak in I4, and then Katschab's and Vision in 2007, they show that for every closed arithmetic Riemann surface, you have a sequence of congruence coverings. So the degrees go into infinity, and the genus obviously is also going to infinity. And the systole, which is the length of the shortest closed geodesic in a surface, is growing with asymptotically with the logarithm of the genus. And that kind of behavior, the kind of growth is optimal up to constant. So yeah, so there's something that is known for arithmetic surfaces. Number three, Vigneura in 1980 used these number theoretic tools to construct isospectral surfaces. They're non-isometric. It means that, so it's been a famous problem. Katz's "Can you hear the shape of a drum?" So when you how much does the spectrum of the Laplace-Beltrami operator determines the geometry of, say, a Euclidean domain, a Riemannian manifold. And the first examples, I believe, were given by Milnor. 16-dimensional, there were 16-dimensional manifolds, but then Vigneura built a bunch of examples, infinitely many examples of isospectral, non-isometric hyperbolic surfaces using these operators of arithmetic groups. And number four, Reed proved that the examples built by Vigneura, although they're non-isometric, they're all commensurable. They're necessarily commensurable. And then in 92, Reed proves that this is always the case for arithmetic groups. So the commensurability class of an arithmetic group is of an arithmetic surface is determined by its Laplace spectrometry spectrum. So when you have two of these guys have the same spectrum, they have arithmetic, and they have to be commensurable, right? And let me just say another item that is not here, but I mean it doesn't really fit into this pattern, but for three manifolds, right? You can also define, same way you define arithmetic Fuchsian groups, you can also define arithmetic Kleinian groups, and then you get three manifolds. And this construction gives you infinitely many, even infinitely many commensurability classes of closed three manifolds, which is something that is it's not so simple to obtain. Of course, the post-Thurston world, we know a lot of hyperbolic three manifolds, but that hasn't always been the case. And this construction gives infinitely examples. That's arithmetic groups, right? So we see here that they come up, for instance, in number one as extremizers of certain properties. In number three, they came up as a rich source of examples. Number two and four, there's some behavior that we not necessarily understand. We don't necessarily understand for a generic surface, but we do understand for the case, the subclass of arithmetic surfaces. But on the other hand, for a fixed genus, at least two, there's a whole moduli space, a whole Teichmüller space of marked hyperbolic structures, and only finitely many of these hyperbolic structures are arithmetic surfaces. So you can see this as one motivation for studying these objects. So you try to find a class of groups that on the one hand is more abundant, and on the other hand still has some arithmetic properties like integrality of traces and stuff like that, some things that might be a bit mysterious. So, right. That being said, let me give you the setting that we're going to be working with. So Blackboard H is going to denote the hyperbolic half plane with the usual metric, and the PSL2R acts on the hyperbolic plane faithfully by orientation preserving isometries. In fact, it's the full group of orientation preserving isometries. And we'll be interested here in Fuchsian groups, so discrete subgroups of PSL2R. And because they're discrete groups, they act, what's it called? Properly discontinuously on the hyperbolic plane. So you can take a quotient, consider the orbit space. It's a Riemann surface, right? I'm going to define later on arithmetic and semi-arithmetic Fuchsian groups, and then when gamma, and this is the case for gamma, we say that this surface is arithmetic or semi-arithmetic accordingly. So these are the objects that we're interested in here, and we can associate to these objects some arithmetic data. So for here on out, I will assume that gamma is finitely generated non-elementary Fuchsian group. And then gamma squared, this, this. The gamma squared is the subgroup generated by the square of every element of gamma. And when gamma is finitely generated, the subgroup will have finite index in gamma. So you take all the traces from all elements of this subgroup, gamma squared, you would join that to the trace of rational numbers, you generate this field, this is called the invariant trace field. And it's called invariant trace field for a reason, is because it's invariant under commensurability. Now, let me remind you that two groups are called commensurable. Well, in this case, they're both subgroups of PSL2R. They're called commensurable when the intersection has finite index in each of them, has a finite index subgroup in each of them. So if you're looking at it from the side of quotients, you have two surfaces or two orbifolds that are commensurable when they admit a common cover that covers each of them with finite degree, right? And I'm not going to go into much detail about this, but in this setting, we're usually looking for to distinguish groups or to define things up to commensurability. It seems like the right equivalence to consider between objects, because some of these things are only well defined up to commensurability. So it wouldn't do us any good to associate an arithmetic object to our Fuchsian group if that is not invariant under commensurability, right? And that's the reason why there's this gamma squared. You might be asking, why not just take the traces of gamma and adjoin that to the rational numbers? Because if you do that, well, then it's not invariant under commensurability. It's one of those things. Right, so you have to do this workaround, and you get this trace field, this invariant trace field that will always be denoted as K, and then gamma is the letter representing the group. So it's an invariant of commensurability. I already said that. And right, that's all we need to define. And it's all we need in order to define arithmeticity and semi-arithmeticity for Fuchsian groups. Now, let me give you a heads up. This definition is going to sound a little bit obscure in the sense that you might ask, why would someone define that and look into these specific kind of groups? But there's the upside is that it's very simple to define and to communicate. So you see just one sentence. That's it. Very easy to communicate. Might seem a little bit obscure, but easy to communicate. So you say that a Fuchsian group is semi-arithmetic when this invariant trace field that you associate to the Fuchsian group is a totally real number field, and all the traces of all elements of gamma are algebraic integers. Now let me just recall here a couple of concepts from Galois theory. A number field is just a finite algebraic extension of Q, right? You can think of Q join square root of 2. Then you can embed this field into its algebraic closure, or you can think of an embedding of this field into C. For instance, if you map Q adjoint square root of 2 into C with inclusion, that's obviously a field homomorphism, right? But you can also map square root of 2 to minus square root of 2, which is another root of the minimal polynomial of square root of 2 over the rational numbers. This is called the Galois conjugate, and this gives you another embedding. Whichever way you do it, you end up with a subfield of the real numbers inside the complex numbers. That's what's called being totally real, right? You can try to do the same thing with the cubic root of 2, wouldn't work, because it's not totally real. And then you require that the traces are all algebraic integers. It just means that it's a root of a monic polynomial with integral coefficients, proper rational integral coefficients. And that's the definition of semi-arithmeticity, right? If, in addition to that, the group satisfies another property, we say that it's arithmetic, right? And this property is that when you look to these so-called Galois embeddings, there's different ways of embedding your number field into C. Every non-trivial Galois embedding maps the set of traces into a bounded set of C. It's this additional property that makes a group arithmetic. So for those of you who already know this definition of arithmeticity for Fuchsian groups, it might not seem too crazy since we're trying to define a broader class of groups, so we just cross out this one requirement and we obtain something that's weaker, as the name suggests, semi-arithmeticity, right? So let me just say here that for these Galois embeddings, some of them, they map the trace set into a bounded subset of C. Some of them map into an unbounded subset of C, and the number of Galois embeddings that map the trace set into an unbounded subset of C, we call that number the arithmetic dimension of gamma. It's going to come up at some point. So another way of saying this is that arithmetic groups, Fuchsian groups, they are semi-arithmetic groups with arithmetic dimension 1, right? Because the inclusion obviously maps the trace set into an unbounded subset of C, and then all other Galois embedding by hypothesis do not. So arithmetic dimension 1. These groups were introduced by Schmutzschaller and Mulford in the year 2000. And let me just observe here that it makes sense to talk about arithmetic or semi-arithmetic points of a Teichmüller space, because one way to look at a Teichmüller space, to define a Teichmüller space, is to look at homomorphisms of your group, like different ways to embed your group inside PSL2R. So you're looking at homomorphisms that are injective and type preserving, etc. And then you quotient by actions, by the action by conjugations in PSL2R. And because we're defining arithmeticity and semi-arithmeticity in terms of traces, and traces are invariant under conjugation, so it's well defined to say that a point in a Teichmüller space is semi-arithmetic or arithmetic. Now, right, so as I said, this might seem a bit obscure, and there are, of course, other equivalent definitions, but I'm not going to go into that because that would be a bit time-consuming. But let me just say that this other equivalent definition of semi-arithmeticity that goes through quaternion algebras over number fields and orders in that quaternion algebra, they end up giving you an embedding of your group gamma, your semi-arithmetic group gamma, into this Lie group here, this algebraic group SL2R, product of several copies of SL2R. And more than that, it embeds your group in a lattice. So discrete subgroup of this Lie group that has a finite covolume. And here I wrote gamma in quotation marks because I'm not being 100% precise here. It's just the idea, like just think of it this way. And see that this R here is the arithmetic dimension that I mentioned before. And so Geninska proved in 2012 that these groups, these embeddings, they take gamma into a group that is Zariski dense, right? So that's, in other words, this embedding realizes gamma as a thin group, which means exactly that it's an infinite index subgroup of a lattice that is still Zariski dense. Right, that's the definition of a thin group, and it's been a topic of research in the past 10, 15 years.
If R is larger than 1, right?
What? Yes, yeah, right. R is larger than 1, yeah. Because R equal 1 is the arithmetic case. Yeah. Thank you. I listed here a couple of examples of results, and for the sake of reference. So Long and Thistlethwaite proved in 2020. They constructed Zariski dense surface subgroups inside of SL and Z inside of SL and R for N odd, and then Audibert in 22 did the same thing for SL and R for all N, at least 3, and a bunch of other Lie groups. And the celebrated surface subgroup theorem that finds a surface subgroup inside a lattice in PSL2C, which is inside a Kleinian group, which is but a lattice in PSL2C. So I think that there's a little bit of a trend here of finding surface subgroups inside lattices in various Lie groups. And this way of looking at semi-arithmeticity, the way following the second definition that I actually didn't give, kind of fits nicely into this. So I'm just giving that as a bit of a reference. It could be also a motivation why you'd want to look into these groups. Right, so I've defined semi-arithmeticity. I hopefully have motivated it a bit, but haven't seen any we haven't seen any semi-arithmetic groups so far. So let me just show that this class is non-empty. Well, obviously it's not empty because they contain the arithmetic groups just by the way we defined it. But that's not interesting because, well, that's cheating. We already had the arithmetic groups. So the second example are the triangle groups, which are groups with this presentation here. It's an infinite leaf family. All of them are semi-arithmetic. Let me just remind you that whenever you have a convex hyperbolic polygon, so a polygon such that the sides are segments of a geodesic in hyperbolic space, in this case a triangle, and when the angles are submultiples of pi, I don't know if this is large enough, but so you can consider reflections across the geodesics supporting the sides. And you can consider the group generated by these reflections, which is a discrete group of isometries, not all of which are orientation preserving. The reflections themselves reverse orientation. But you can also look at the index 2 subgroup of orientation preserving isometries here. And this is a Fuchsian group that has exactly that presentation. You see, it depends on, so the order of the generators M and L, they depend on these angles here, and on nothing else. Because when you choose the angles, you determine the triangle and you determine the Fuchsian group. And because it's a somewhat simple case, you can compute some things explicitly, and you see that all of these guys are semi-arithmetic. So all of them have integral traces, and all of the invariant trace fields are totally real number fields. And yeah, it's an infinite family. And Takeuchi proved in the 70s, 76 or 77, that only finitely many of those can be arithmetic. 85, I think. So almost all of them are strictly semi-arithmetic, meaning they're semi-arithmetic, non-arithmetic groups. So this shows that the class of semi-arithmetic groups are actually like strictly larger than the class of arithmetic groups, right? Another source of examples would be we can try to do the same thing that we did with the triangle with this other hyperbolic polygon, sort of the next best thing. It's called a tri-rectangle because you see it has 3 right angles and 1 acute angle that I am fixing to be pi over 3. It's not necessarily pi over 3, just like a choice there. Sorry, I cannot hear this. No, they go to infinity, yeah. So this is going to come up later. Go to infinity. That's a good point, yeah. So in these tri-rectangles, see this in this picture, there's sort of this is, I'm thinking of this as the origin of, and then the Poincaré disk. You see, these are geodesics. And we can play the same game, get reflections, generate a group, look at the Fuchsian group. And the main difference here is that for triangle groups, the representation variety of these Fuchsian groups, they are 0-dimensional. So in this case, the dimension is positive. So for instance, you could vary the lengths of these sides. You could vary the lengths of these sides. But there's this very elementary formula here in hyperbolic geometry, that relate the trace of a hyperbolic element to the translation length of this hyperbolic elements. And even though it's a very simple formula, it sort of connects on the one side the arithmetic information, on the other side the geometric information. So I defined semi-arithmeticity in terms of traces of elements, and the traces are related to translation lengths, at least for hyperbolic elements. Some of these translation lengths are related to the lengths of the sides of this polygon. And because I fixed the acute angle as pi over 3, they're hyperbolic trigonometric relations that bound all these lengths together. So once you determine A, for instance, you choose A. Sorry, once you choose A, you determine all the other lengths. So you choose A, you determine all the other lengths. So you determine translation lengths of hyperbolic elements. So you determine traces of lots of hyperbolic elements. And it turns out that this is enough, this is sufficient to say if the group is going to have a totally real number field, invariant number field, and integral traces. Yeah, so the idea being that if you choose A well, you can guarantee integrality of the traces, and you can guarantee the invariant trace field is going to be totally real. And you can actually do that. But yeah, so moving on to another polygon, we can easily obtain another result with the right-angled hexagon, and that's because, see, we can tile this polygon by the tri-rectangle. This is the tri-rectangle that we had in the previous slide, and this is a right-angle hexagon with 3 non-adjacent congruent sides. So again, because you can tile the hexagon, so if you choose an A, a parameter A, such that the tri-rectangle is semi-arithmetic, it generates a semi-arithmetic group, then you can obtain this hexagon, and the group generated by the hexagon will also be semi-arithmetic. And the upshot here is that these hexagonal groups, they contain surface subgroups of every genus, right? So that's the reason why I want to look at the hexagon. So in fact, if you consider calligraphic A to be the set of parameters, positive real parameters that you're choosing from, if you consider this calligraphic A to be the set of parameters that lead to a semi-arithmetic group, this set is actually dense in the positive reals. So yeah, so you choose any of these parameters, you get a semi-arithmetic H. This calligraphic H, I'm using this to denote the group that you obtain from the hexagon, and 2A is just because this side is going to have length 2A, right? And that gives you a semi-arithmetic surface inside this group of genus G with a closed geodesic of length 4A, I think 4A, but anyways, something times A. So you can say that, so if you fix the genus G, at least 2, you have the whole Teichmüller space. You can look at the underlying topological surface of genus G, and you look at a non-trivial free homotopy class. Whenever you vest the surface with a hyperbolic structure, there is one and only one geodesic in this free homotopy class, non-trivial free homotopy class, and you can measure the length of this geodesic, right? So that gives you a positive number. So for every point in a Teichmüller space, you have a positive number. That's the length function. And what we're saying is that you can find a length function here. You can find a free homotopy class, non-trivial free homotopy class, such that that gives you a length function that maps all semi-arithmetic points in this Teichmüller space into a dense set of the positive real numbers, right? So in particular, you have infinitely many semi-arithmetic points in that Teichmüller space, right? There's something else I wanted to say here. All right, a couple of consequences of this construction. Is that one of them is that you can find for every fixed genus, you can find infinitely many totally real number fields of arbitrarily large degrees, if you want, that can be realized as invariant trace field of a semi-arithmetic Riemann surface of genus G. And that was once conjectured not to be true, because, I mean, we knew before that you can realize infinitely many number fields as invariant trace fields of semi-arithmetic surfaces, but you had no control over the genus. And it was conjectured that for a fixed genus, if you fix a genus, you could have like at most finitely many totally real number fields being realized, and this construction shows that you can have infinitely many. And another consequence is that when you look at the systoles of semi-arithmetic Riemann surfaces, you consider all of them together of all genera. The set of systoles is dense in the positive real numbers. You know, it comes from the theorem in the previous slide, because that gives you a closed geodesic with a length that approximates any number that's not necessarily the systole, but then you can look at covers of this surface, right? So there's two consequences. And okay. So I've defined semi-arithmetic Fuchsian groups, and I showed to you that there are lots and lots of them in every genus. As I said before in the introduction, for arithmetic groups, if you bound the co-area, so for instance, if you fix a genus, there are only finitely many of them. So if you bound the co-area here, you still have infinitely many semi-arithmetic groups. So one thing that we're interested in is what other invariants can you bound and should you bound in order to have finitely many semi-arithmetic objects. And then there's this list of finiteness results. Going back to Takeushi's result that I mentioned previously. So he proved in 76 that among the triangle groups, only finitely many of them are arithmetic, right? Then Borel proves something that sort of generalizes that, is that if you bound a co-area, so Takeuchi is looking at specific signatures, namely those of triangle groups. Borel is looking at all the signatures, and he says that as long as you bound the co-area, there can be only at the most finitely many arithmetic groups. And Nugent and Voigt, they generalized Takeushi's result directly in a sort of another way. So they're still looking at at triangle groups, but then they're looking at triangle groups that have a bounded arithmetic dimension, right? That is that invariant that I mentioned earlier. And also here you have finitely many triangle groups with finite arithmetic dimension, right? So in Borel's result, you're looking at you allow various signatures, but you're still looking at objects of arithmetic dimension 1. In Nugent and Voigt's result, you allow arithmetic dimension. You're bounding the arithmetic dimension, but you're still confining yourself to the class of triangle groups. If you try to merge these results together, these two results together, well, 3 results together, then you can ask if you have semi-arithmetic groups with bounded co-area and bounded arithmetic dimension, is it true that in general you're looking at all signatures at the same time? Is it true there are only finitely many? And it isn't. You can find infinitely many non-commensurable semi-arithmetic groups having the same the same covariant, the same arithmetic dimension. It's also a construction with a dry rectangle that I showed earlier. And this proves that you need to bound something else here. And in an attempt to generalize that, we proved, in joint work with Billy Lipitsky, Doria, and Teixeira, we proved that if you bound the coarea, the arithmetic dimension, and this stretch, which is a commensurability invariant that we defined, then there can be at most finitely many semi-arithmetic Fuchsian groups. So let me talk a little bit about this this invariance. So in order to define this invariant, let me talk about modular embedding. So what is modular embedding? When you have a semi-arithmetic Fuchsian group, you have a family of embeddings of this gamma squared into this Lie group, SL to R to the power R. And this actually appeared before in a previous slide. It was that when I wrote with a quotation marks, it was being a little bit imprecise. So you have these embeddings coming from the definition of semi-arithmeticity, right? So gamma squared acts on the hyperbolic plane, and the right side, the Lie group on the right side acts on a product of R copies of the hyperbolic plane. And you have this homomorphism, injective homomorphism, right? So you say that gamma admits a modular embedding if there is a holomorphic, if there is an F equivariant holomorphic map from H to a product of R copies of H. And being F equivariant means exactly this, that if you act on the argument of the function and then apply the function, it's the same thing as if you apply the function and then act on the image of the function, you know. So, yeah. And it turns out that this is a very specific property that has consequences, like algebraic consequences. And it's not every group that admits a holomorphic map like that. So what we try to do is that we try to ask for an F equivariant map that is not necessarily holomorphic, but it's Lipschitz, right? And then the best Lipschitz constant that you can have that would be the stretch of your group. So let me just say, so which groups admit modular embedding? So arithmetic, let me go back here. Arithmetic groups, they admit modular embedding like quite trivially, because then when the R here is 1, then you have the inclusion here, and you can take F to be the identity, so that would be modular embedding. And the triangle groups, they also admit a modular embedding that you can construct using complex analysis, and you use very much the fact that this polygon is a triangle. So yeah, so you have modular embeddings for these guys too. And in fact, as far as I know, it's still not known if there are co-compact Fuchsian groups admitting modular embedding. They're neither arithmetic nor are subgroups of a triangle group, as far as I know. And these holomorphic maps will be one Lipschitz, right? So in the finiteness results here, since Takeuchi was only looking at triangle groups, so these groups, they had bounded stretch because they admit modular embedding, and all triangle group has coarea bounded by 2 pi, right? Borel was bounding the coarea and looking at arithmetic groups, so also bounded stretch incidentally, and then Nugent Voigt, again, looking at triangle groups. So it turns out that in all these three cases, they're bounding the arithmetic dimension, the co-area, and the stretch. And that's, we show that that's exactly what you need to bound in order to obtain a finiteness. And yeah, so that's the definition of stretch that I said. I don't like the way that this is phrased. I think it's, the way I said it sounded better. And yeah, this is what I just observed. So yeah, so the finiteness theorem generalizes this for semi-arithmetic groups in general. How much more time do I have? 5 minutes? 5 minutes?
5 minutes.
Okay.
7 minutes.
Okay. Okay. So let me try to give some of the ideas. I'm not going to have enough time to talk a lot about ideas, so I don't know if I should start talking about ideas, but yeah. So just let me say a few words about kind of results that we used here. So what we're trying to prove here is finiteness, the finiteness theorem. So when you bound the co-area, arithmetic dimension, stretch, you get finiteness. So we start with the torsion-free group gamma, and the first step is to prove that the degree of the extension of the invariant trace field of gamma over K is bounded in terms of the bounds that you're already given by hypothesis, right? And in order to do that, we use this arithmetic Margulies lemma. It's a recent theorem by Verchuk, Hurtado, and Rambol. And it's, well, so I don't know if that's it's a good idea to make calculations here in front of everybody, but so what we're trying to do, it's so if I in the geometry of your group gamma, you find two hyperbolic elements of a certain minimal displacement, of a certain translation length, let's say R, that they have disjoint limit points. So in particular, the group they generate is contains a free group, right? And right, so as I said before, when you have a semi-arithmeticity, you have a way to embed these guys into a lattice in a Lie group, SLR to the power R. Now, because the Lipschitz constant, the stretch, is being bounded, so the displacement of the image of these two elements are they're at most L times R, right? So so then perhaps I should write this here. So you have the how do I call this? So rho star, I think that's the notation I used, of gamma I of pi, of gamma I of p. Let me think. Right, so yeah, and p, this distance. So I think I used F, right? It's going to be something like L times R, where R was the distance, hyperbolic distance of gamma I of a point and the point, right? So so yeah, so this should be, remember we have an equivariant map, so this should be F of pi. And yeah, so now because of equivariance, we have that. So this right? But then the image of these two guys inside the lambda in this theorem, we know that they generate a group that contains a free group, so it cannot be virtually solvable, virtually nilpotent, sorry. So it means that one of these, either gamma 1 or gamma 2, violates this condition here, right? So for one of them at least, let's say gamma 1, this is going to be greater than the constant that only depends on G times the trace, the degree of the trace field. And because this is, as I said, this R depends on the geometry of the fundamental group of your gamma. So this is the radius of a ball. And because of the radius of a ball in a hyperbolic plane is pretty much exponential, the area of the hyperbolic disk is pretty much exponential. The radius, you can think of this as being L times log of the area of the ball, area of the disk of radius r in the hyperbolic plane. But this disk is circumscribed in the fundamental domain. So this is less than the area, the whole co-area, which is by hypothesis bounded by n, by mu, sorry. And this shows that there is a bound for the degree of the invariant trace field in terms of all the other bounds that you have. So that's the first step in the proof. You assume bounds on these invariants, then you bound the degree of the invariant trace field, and then you bound, you use this to show that the systole of these groups is bounded from below, so you're actually in a compact part of the Teichmüller space, and then little by little you show there are finitely many of these guys when they're torsion free. Right, and then when in the general case, you have to look at the signatures and you have to look at the implications of these bounds on the possible signatures that you can have. And well, I think that's I think that's all I'm going to say about this. So I'm going to skip the rest here. And thank you. Yeah.